Thanks for organizing this great workshop, and thanks for inviting me. I really learned a lot from all the speakers here. So my talk is, as the title suggests, is actually based on like the data that we have, what type of learning can we do? Like, I mean, the reality versus, I mean, the theory. So the talk will be mainly on MR reconstruction, but the ideas can also be applied to different imaging modalities, such as CT or other ones. So let's start with the recap of actually MR reconstruction. So as we have seen actually in earlier talks, so the forward model for MRI acquisition is as follows. Here we have an acquired measurements from a scanner denoted by Y, and omega is sampling pattern, and E is our encoding matrix that contains multiple information such as Fourier operator, and then we have measurement noise. This problem is usually ill-posed, and we solve a regularized least square problem consisting of two terms. One term is the first term is data consistency that makes sure that we are consistent with what we get from scanners. The second term is a sparsity promoting regularizer. And as we have seen, there are a lot of approaches that we can actually use to solve this problem. Some of the popular ones would be proximal gradient descent and also the variable splitting approaches. And so the question is, how can we learn a regularizer? Well, in the conventional methods, what we do actually is to iterate between a regularizer and a data consistency unit until we hit a stopping criteria. And this regularizer is often a fixed linear spacing transform, such as wavelet. And we learn actually parameters such as the penalty one by hand tuning. And as we have seen also in other talks, we can actually now also use deep learning to learn a regularizer. What we can do is actually to take this iterative approach and unroll it for a fixed number of iterations, where in each iteration we have a regularizer and data consistency unit, and our regularizer can be replaced with the neural networks. So, and for our network, like the parameters can be either shared or different across the unroll iterations. So the first scenario is if you have lots of data that is labeled, for example, fast MRI data set, we have labeled data, then we can actually use supervised learning. And the idea is actually you can use the ground truth as reference. And what you try to do is actually to minimize the loss function, like over this large database between a reference image and also a network output. And the ultimate goal is to learn those parameters that will help us in the inference time. So how the training mechanism works is actually as follows. So you take this undersampled image that has lots of artifacts, and you input it to a network. It can be either a neural network or just a neural network. And in each one of those units, we have like a regularizer, like neural networks, and our DC units. And DC has access to the physics of the problem. Like we have sensitivity maps, sampling pattern. But what we get is actually the network output. And since we have actually a reference, we can know how well we are doing in terms of the reconstruction. So we can compute a loss and update our parameters. So there has been actually lots of work in this domain that uses supervised learning, because if you have the reference, you can compute the loss and you can do lots of things. So one of the first work in the field was a variational network. What they did actually was directly unrolling the gradient descent by using the field of expert model. And they show that you can actually perform better than the conventional methods, parallel imaging and compressed sensing. And so the follow-up work actually replaced the variation networks with the convolutional neural networks. Here you can see a cascade of neural networks followed by data consistency. And they also showed actually you can perform really good reconstruction quality. But one of the main problem would be is, so you can do supervised method if you have a reference. But in many scenarios, we don't have that. So one of the examples is organ motion. Or if you do the high resolution MRI, the scan time becomes excessively long. In diffusion MRI, signal decays quickly, so you don't have a reference. And overall, it's impractical and it's costly. So the question is, if you don't have that reference, how can you compute the loss and update your parameters? So to tackle this problem, now we can actually go from supervised to self-supervised. And we propose actually an approach, like a self-supervised learning approach. And idea is that, again, so what you have is this acquired location. Let's try to do learning from here. So we can actually take this acquired case-based location, denoted by omega, and split them into two sets, namely theta and lambda. Theta is used in the data consistency in the unrolled network, and lambda is used to define the loss in the measurement domain. And these two sets are disjoint from each other. This approach is known as SSDU, which stands for self-supervision via data undersampling, and we can actually check our loss function. It differs from the supervised learning in a way that we define the loss on the unseen measurements, which is our second set lambda. But the training mechanism is similar. You still have undersample measurements going into your neural network. You still have your like unrolled network, again, Regularizer and DC. But DC has access to a subset of the measurements now. But this is okay. Like, you can still get a good network output. But what we can do now is actually transform our network output to the measurement domain at those unseen locations lambda. And now we can actually compute the loss. And based on the loss, you can update your parameter. So, like, not having a fully labeled data is okay. Like, you can learn from only undersample measurements. And this is the situation in lots of cases. So now the question is, does it work? So we did actually lots of experiments on a fast MRI data set to compare it to the supervised learning to see how well we are doing. So here are like some results on fast MRI at rate 4. So the first two, the TG-Sense and TGV are the parallel imaging and compressed sensing methods. At rate 4, they don't perform well. And we can see those artifacts with the red arrows and also the difference images. So supervised deep learning has access to the fully sampled data. That's why it can learn and can remove the artifact. But the interesting thing here is our self-supervised approach that trained only using undersampled data, but can still match the performance of the supervised deep learning. And this is actually the case where self-supervised learning becomes like important. So if you have prospectively subsample data, so we don't have reference data, then we cannot employ supervised deep learning. So like now we have a kind of one option is using parallel imaging method, but they are clinically at rate 2. And rate 2, the reconstruction still has actually noise. And if you want to kind of accelerate the reconstruction, you go to like rate 8, you can see huge noise amplification. And we know that they can't be used in the clinical studies as such high acceleration. But in our self-supervised learning setting, at rate 4, we already achieve a very good reconstruction quality. This is already a twofold gain. And even though we go to like at rate 8, we still don't suffer from such noise amplification. And we actually did the validation study with the radiologists that show that actually our results at rate 8 is better than the clinical study at rate 2, which is a fourfold gain. Well, so far, like we said, if you have labeled data, if you have unlabeled data set, but what if you don't have a data set, which can be actually the situation as well. So, and the reason is like due to those physiological and physical constraints. So we cannot actually acquire a very like high quality database due to like contrast uptakes or like different breathing patterns. And as we have seen in different other talks, that there is a move towards processing larger 3D and 4D volumes. And for those data sets, we don't have a data set for those cases. And another problem is if you train a model like on a certain setting, and if you're in the test time, if you have a different parameter, then your model starts to perform like its performance degrade. And some of those cases are actually in the latest test MR challenge, they show with the vendor. And then the other case could be like SNR, mask, sampling rate, and also, of course, anatomy. So what can we do? Actually, we can now go from a database to a single slice, a single patient. So, and this approach is like zero-shot self-supervised learning. We do not require any external data set. So we perform training and testing using only like the single slice you have or like single image. And therefore, we are agnostic to any change in the distribution. And this has the potential for high quality reconstruction for every individual. At the end of the day, we want to like not only generalize, but we also want to ensure for every patient a good reconstruction quality. Of course, the zero-shot self-supervised learning will have a drawback, long inference time. But we can actually leverage the transfer learning for the computational efficiency. I would like to actually touch upon this paper, like deep image prior. This paper back in 2018 showed that you can actually perform reconstruction or image restoration using only a single image. Here we see like a snail, and you just use a single neural network. As you go through the neural network, at one point you will achieve an optimal reconstruction quality. But if you just keep training on a single image, you will eventually overfit. So what Deep suggests is stop early. But the question is, how can you stop early? Because in the database deep learning, we have a validation set and we can observe it and then we can know when to stop. But if you have a single image, how can you validate? So to address those problems and apply to the MRI reconstruction, we propose this zero-shot learning case. So now that you have a single slice, what we propose is actually to take those acquired case space locations and set aside a validation set. And then the remaining measurements, we can now do training. What we propose here is actually to retrospectively undersample it into training and loss mask. So we are doing it like K times. And the reason is we have a single slice and we still have lots of parameters to learn. So that's why we need a data augmentation here. But now that we have training mask, loss mask, and validation mask, we have actually all the ingredients to do the reconstruction on a single slice. So first we can do the training, and you can see the training loss decreased nicely, but it doesn't tell us when to stop. But now we can leverage the validation loss. You can actually see the validation loss first decrease and then start to increase. And this is exactly what we want to observe. The moment we hit the lowest error on a validation set is actually our stopping point. And now if we actually check the results, so the first situation could be like your train and test data is from the same distribution. So there is no change in terms of parameters. So in such cases, if you take the supervised deep learning and apply it, it's going to work well because there was no change. And deep image prior had this overfitting issue, but our zero-shot self-supervised learning approach can achieve like a comparable reconstruction quality with supervised deep learning, despite being trained on a single slice. And now, but if we come to this reality when your train and test data is from different distribution, then this is where actually supervised deep learning starts to significantly degrade. So one of the examples could be is like you train the model at a specific rate, such as rate 4. And during test time, you want to apply to a higher rate, like rate 6. You want to decrease the scan time further. But what happens actually, supervised deep learning cannot actually tolerate that, and it starts to fail. You can see those artifacts shown with the red arrow. And whereas our zero-shot learning approach doesn't actually have problem with that. And you can just actually achieve a very good reconstruction quality, even though you change the acceleration rate. And another extreme case is you take a data, for example, train on the brain, and during test time, you want to apply to the knee. Well, supervised deep learning, again, doesn't like that, and you can see the artifacts. Whereas, again, in the zero-shot learning, you can do the reconstruction on the fly, and you have good reconstruction quality. So what we show that actually, your data has you have different options. You have labeled data, you can do supervised learning. If you don't have labeled data, do self-supervised learning. And if you don't have even a data set, you can do zero-shot learning. Of course, there are some other learning options like semi-supervised learning. You can also do those. But there are also some practical considerations that we need to put have it in mind. Is one of the main things is how we design those loss functions. We tend to use those L1 and L2 loss, but using perceptual losses would be is really important because it might be closer to human perception in how we actually see those images. And also the metrics. So again, we are tend to use those quantitative metrics such as STM and NMSE, but we know that they can't capture like the pathologies and other like important things. And so that's why if we have opportunity, like want to validate our results, like we should like use the reader, like we should consult with the radiologist and put it into our result. But if this is not possible, of course, like using new metrics such as precision and recall to see how many like pathologies we recover is really important to validate our result. And that will be actually the end of my talk. Thank you. And yeah.
I see a question here.
Very nice talk. Thank you. I was curious to what extent masking strategies affect your results, and if you have any thoughts on creative ways to mask to create the two samples.
So can you actually repeat the question? Thank you.
Yes. Oh, sure. I was curious how masking strategies impact your method's performance. Can you do your masking creatively to enhance some either overall performance or image characteristics?
Yeah, that's a great question. So the way you create your mask actually is really important. So we actually did an empirical study here. So one of the ways actually to create those masks using like Gaussian undersampling, because at the center we have like high energy. So but what we realized, if you go to high acceleration rate, like such partitioning is actually now start to like you're getting a lower reconstruction quality. So what we realized actually the best way is to do uniform random undersampling that makes sure that you have both low frequency and high frequency in your both masks. Yeah.
I think we can move on since to the last talk that separates us from lunch. I don't want to push us too far back. So thank you.